Hi, this is Kevin Trainer, and welcome to my lecture for Chapter 8 of the Zelle 3rd edition Python book. And this is going to be part 1 of the lecture. There'll be 2 parts. This is a pretty long chapter. It's kind of interesting because Chapter 5 was pretty extensive, and it was about sequences. And Chapter 8 is primarily about loops. We've learned a little bit about loops previously, but we're going to learn a lot about loops here. And it's the loops that you use to process the sequences. And so they have kind of a complementary kind of aspect, Chapter 5 and Chapter 8. And the fact that one's kind of big and then the other would be big too, well, not too surprising. So here we go on part 1 of 2. Okay. So I'll leave you to read the objectives on your own. Okay. So, we've been using for loops for a while, and we're just going to do a quick review of what we know so far. So the for statement allows us to iterate through a sequence of values. So we can say for variable name in sequence. Okay. And then we have a body of code that gets executed for each of the items that is in the sequence. And you'll remember we've got 3 kinds of sequences that we worked with. Strings have a sequence of characters. Lists have a sequence of items in them. And files have a sequence of lines of text in them. And we found that this for in structure worked for all 3. Okay. So the loop index variable var in this case takes on each successive value in the sequence. And the statements in the body of the loop are executed once for each of the values. Okay, so I just want to remind you before we start to look through examples, this chapter takes the typical approach of kind of walking us through some potential approaches, okay, that turn out not to be our final choice, okay? And that's because typically we in teaching think it's often good to kind of explore the alternatives before you pick the last one, or certainly the first one that you're going to give serious consideration, because it's important to know that that one that you choose in the end has a lot of merit to it. So we're going to look at a couple of things that we're not really going to do on a regular basis. Okay? So take that warning. So suppose we want to write a program that can compute the average of a series of numbers entered by the user. Well, we've done things like that before. To make the program general, it should work with any size set of numbers. So far, we've just, for the most part, we've had a fixed length set of numbers, which is not very general. There aren't a lot of times that you need to add exactly 10 integers. Okay? more likely that sometimes you're going to want to do 3 and sometimes you're only going to do 23. So we don't need to keep track of each number entered. We only need to know the running sum and how many numbers have been added. That's because we need to compute the average, and the sum of all of the entries divided by the number of the entries is going to give us the average, or the simple mean. We've run into some of these things before. So a series of numbers could be handled by some kind of loop. If there are n numbers, the loop should execute n times. We need a running sum, and to do that, we'll use an accumulator. So we've already seen the pattern of using an accumulator. Okay. Well, okay, so here's some pseudocode for it. Input the count of the numbers. So we're going to prompt the user at the console for the count of the numbers. And we're going to call that n. Initialize the sum to 0. That's part of the accumulator pattern. Loop n times. Input a number x. Not a really well-chosen variable name, but we'll take it. Add x to the sum. And then when we're done, when we've finished the loop, we're going to output the average as the sum divided by the count, n. And, again, I'm not sure that n is a well-chosen variable name for you and I. For you and I, we always want to choose variable names that are descriptive without being too wordy. So these algebraic variables are kind of interesting, and I think appealing to the author because he has a mathematical background. But for instance, you wouldn't use variable names like these on the job. They're they're not sufficiently descriptive. Okay. Oh, I keep hitting the wrong button. Sorry about that. So here's what we have. So this is called average 1, as though there's going to be a series of them. And in the main, what do? Well, we get an int for how many numbers do you have. We initialize the sum to 0. Then we say for I in range n. I don't know if we've really done this before. But typically when we've done a range in the past, we've used a literal value there. And the fact is you can use a variable name. So you can actually ask, well, how many do you want to input? And use the range expression to get the number that you want. And so what are we doing? So for each of the iterations, we are reading a number. It looks like we want a floating point because we're converting it with float. We're putting that into x, and then we're accumulating it into the sum. Now you might say, well, don't you have to accumulate the count as well? And I would say, well, because the fact that we determine what the count is going to be in the beginning, instead of accumulating the count, we're just going to be able to assume that it's going to go up to n. So when we're done with the loop, we'll be at n. Okay? And then we're going to print a new line, and then the average number is sum divided by n. Okay. Now, what do we like about this? Well, we like about this that we can add a group of numbers and not have to know way ahead of time when we write the program how long the column that we're going to be adding is going to be. What's not good is that you have to tell at the beginning how many they're going to be. If you ever used an adding machine to add up a list of figures, you'll a lot of times you'll have like a page and a half of them. Well, how many entries are on a page and a half? Well, you're probably going to have to count them by hand. Okay, so this is better than just having a program that will count, say, 10 or 5 or 3. But having to count by hand the number of entries that you have before you begin to process them, it's still not an ideal solution. That's why we're not going to land on this solution. We're just going to experience it and go on to the next version. Okay, so in this case, how many numbers do you have? 5. We get prompted 5 times. We do the calculation. So pretty straightforward stuff. Okay, so that was what we call a definite loop, the one that we just did. Okay, we picked a number of times we were going to do it, and we did it. Now, it was a little more flexible that we'd seen before because we prompted the user and said, well, how long of a definite loop do you want? And, they could say 3 or 300, and we would do it that many times. But as I was saying earlier, if you're really using this, to get the average of a column of figures in the real world, you don't want to have to know ahead of time how many you have. It's just inconvenient. Okay, so what we need is a way for the computer to take care of counting how many numbers there are. The for loop is a definite loop. That's what we've learned already. The for is a definite loop. Even if you are counting up to or down from a value that you asked to get from the user, okay? When you begin the for loop, you know definitely how many times it's going to execute, okay? Now, we're going to talk about indefinite loops, which is pretty much what this chapter is about, the varieties of those. So we can't use a definite loop unless we know the number of iterations ahead of time. We can't know how many iterations we need until all the numbers have been entered. Well, if we count them by hand, it's inconvenient, but it can be known. So we need another tool. So there's another kind of a loop, somewhat more sophisticated one called indefinite or conditional. That keeps iterating until certain conditions are met. Okay, so it's going to keep going indefinitely until some circumstances come to be, in which case it's going to stop. Okay, I keep hitting the wrong key. I apologize for that. So here's the syntax. While condition, so we know conditions because we coded them in when we were working on the if, the else, and the else if, right? So we say while condition colon, and then there's a body. So as long as the condition evaluates to true, we'll continue to iterate over this and execute the body over and over again. So the condition is a Boolean expression, just like in if statements. The body is a sequence of one or more statements. Semantically, the body of the loop executes repeatedly as long as the condition remains true. When the condition is false, the loop terminates. So here by semantically, we mean by the meaning of the statements. So the meaning of the statements implies that it's going to continue to execute until condition becomes false. Okay? Okay. So this is the most popular version of an indefinite or conditional loop. It's called the while in Python. And one thing that's really interesting to know about the while is it is a pretest or test before loop. So here they're showing us the programming flowchart for this construct. And as you can see, you come into the construct. The first thing you do is you run the test. Okay? So it's possible to fail the test the first time you come into the loop and never execute the body. Okay? It's only if you pass the condition, only if the condition is true the first time you test that you'll do the body even once. Okay? So it's possible to execute 0 times. Now, it turns out that for processing sequences, this is really well matched to what the job is, because it's possible for sequences to be empty. Let's just think of the sequences that we have, okay? So one kind of sequence is a character string. Is it possible to have a character string with 0 characters in it? Yes, the empty string, okay? The next kind of sequence that we learned about is the list. Is it possible for us to have an empty list? Yes. And then the last kind of a sequence that we learned about in Chapter 5 is a text file. And is it possible for a text file to have no lines of text in it? Yes, it is. It's possible for that to be empty as well. So given the fact that these sequences can be empty in the trivial case, a very important case though, it turns out that these while loops are just perfectly suited to processing sequences, okay? Mainly because they test before. So we won't accidentally start to do the work in the body in the occasional condition that the sequence that we're processing is empty. Okay, so here's an example of a while loop that counts from 0 to 10. So we have to initialize the control variable. I gets assigned 0, while I is less than or equal to 10, print I. Now here's a really important part of the loop. This is the first one we're building. We have a statement at the bottom of the loop that changes the state of the control variable. So we say I gets assigned I plus 1. Okay? Now why is that important? Well, because if we come into a while loop and we pass the test the first time that we the first time through, and then we do the work, if we never change the value of the variable or variables that are used in the test expression, it will be true forever. So we will have an infinite loop, which we'll explore in a couple of minutes. So it turns out that this while that we built really functions the same as the for loop we see at the bottom of the slide. For I in range 11, print I. Okay, so you'll remember that when we say range 11, 11 is the first value that we don't want. Okay, so it's going to print from 0 through 10. And that's what this does. It starts at 0 and it prints up through 10 because it's less than or equal. Now, if we had a choice between expressing a definite loop the top way or the bottom way, I would consider it better practice to express it the bottom way. It's more succinct, it's easier to read, it's easier to understand. Okay, but this is just an exercise where we're saying you can take any definite loop and you can express it with a while. It's a very general construct. You just have to remember to initialize the control variable before you get into the loop. Okay? So the while loop requires us to manage the loop variable I by initializing it to 0 before the loop and incrementing at the bottom of the body. If the for loop, in the for loop, this is all handled for us automatically, which is why, again, it would be the choice if that's what we were trying to do. The while statement is simple, but yet powerful and dangerous. While loops are a common source of program errors. Okay, so one error that can happen is the dreaded infinite loop. So we say something like this. We say we initialize I to 0, and then we say while I is less than or equal to 10, well, we're going to pass that the first time through. We're going to print I. We never increment I at the bottom of the loop. What happens? What we call an infinite loop. When Python gets to the loop I is equal to 0, we went through that. This is going to go on infinitely, right? What should you do if you're caught in an infinite loop? It says first try pressing the Control C. That's a typical operating system shortcut for stopping the program that's currently running. If that doesn't work, try Control Alternate Delete. A lot of times that's a way to reboot your operating system. If that doesn't work, push the reset button. Okay, so it is possible to get into a loop that's very, very tight, a very small amount of code. And it is possible on some computers to get to the point where the computer isn't even listening for you to interrupt it with any of the signals, like any of the keyboard-oriented signals, okay? You might have to turn your computer physically off. Now, for us, we're using PyCharm in our course. So what I did is I made ahead of time a program. I put this into my mad computer scientist experimenter project that I call Frankenstein. And it's called an infinite loop. And it gives me an opportunity to show you a construct that's pretty interesting. We have while, and then we have a condition. Normally, the condition that we have is a comparison, right? But it turns out that you can use the Boolean values true and false. So if we say while true, this will run forever, okay? And so while true, we're going to print, I have fallen into a loop and I can't get up. That's an homage to some very popular television advertising. Okay, so let's see what happens if we run this. So we're going to run an infinite loop. And you can see it down here at the bottom. It's just printing and printing and printing. Okay. Now, what's the way that we stop an infinite loop on PyCharm? We come over here to the left of this console that we're using to run the test, and we click on stop and look at it. It says stop an infinite loop, and it looks like it's saying on the Mac it's Command F2. So I'm just going to click here, and it says, oh, I've done a keyboard interrupt. Process finish with Xcode 1. Okay. So it'll go on forever. Now, we discovered within the last week that right now in the current semester, the version of PyCharm that we're using on Windows 10, when you click on that stop button, it doesn't really sense it in the same way that it's being sensed in the Mac OS and the Linux versions of PyCharm. But I've gone and tested this, and it does stop the program. It doesn't give us this pretty interrupt-oriented text, but it will stop, and it will say process finished with Xcode -1. Now, I would think that maybe by next semester that's going to be fixed. So whether you're going to see the behavior that I showed you here, or the behavior that I described is currently happening on PyCharm on Windows 10, is really going to depend upon how quickly they fix the bug that I think has already been reported. Okay? So that's how you get yourself out of an infinite loop. So you're going to say to yourself, well, I'm not going to create an infinite loop. Okay? So here's what happens. You do. Okay? You do, you will, and you'll occasionally do it throughout your career. Okay? What usually happens here is you do something like this. It's a little more, what can I say? It's a more sophisticated mistake. What if you did this? What if you said, I'm going to use I as a control variable, and I'm going to initialize it to 0. Okay? So I could say while I less than or equal to 10. Okay, that looks fine. Okay, and now at the bottom, I'm going to have to increment the control variable. So I say I plus equals 1. I'm going to increment it by 1. Okay, that looks okay. If we run that, you would think it's going to run 10 times. And it does. It runs 10 times. That's perfect. What if you accidentally hit the minus here? You weren't thinking, you were distracted, whatever is going to happen. Well, let's see what you get with that. You get an infinite loop, okay? Because I is getting lower and lower, it's never going to be higher than 10, ever, okay? You have all the parts of the loop that you need. You've initialized the control variable. You do have a test. You are changing the state of the control variable at the bottom of the loop like you're supposed to. You're just changing it the wrong way. Okay? The other thing that you can do is you can do the opposite. You can change it the right way and have the test be wrong. Okay, so um, uh, new programmers often say, "Well, I'm going to do that one time at most," and I know I've done it at least once in the last year. Okay, so be humble. Okay, so we're going to use the stop button as the way to solve that problem. Okay, and I'm going to go back to my original version of this, which is so let me make sure this it still runs badly. Yeah, there we go. All right, that's good. All right, infinite loop. All right, um, there we go. And the last thing that they're saying here is if in fact you have a program that is stuck in an infinite loop, you may have to do something drastic to stop the program. You may have to hold down the on-off button of your computer. Okay. In our current environment, that's not true, but in some other environment, that might be true. Okay. Um, Infinite loops can get really ugly. Okay. The infinite loop, we've taken care of that. Now, one good use of an indefinite loop is to write interactive loops. Interactive loops allow the user to repeat certain portions of a program on demand. So by interactive, we mean we're going to be working with the user at the console. Okay. So we're going to be prompting them for input. And then the question is going to be, well, when are we going to stop? Right? So remember how we said we needed a way for the computer to track how many of the numbers had been entered. Let's use another accumulator called count. Okay. And it's kind of funny. He doesn't actually differentiate between a counter and an accumulator. And perhaps in some kind of a mathematical sense, they're part of the same thing. But in my mind, a counter is something that you bump up, you increment by one every time through. And so you initialize it to 0, and then every time you go through the loop, you add 1. Okay, you increment it. On the other hand, an accumulator, like the sum, is something that we initialize to 0, and then we add whatever amount we're getting out of the sequence to the accumulator. So I think they're closely related, but they're not really the same thing. So I would call that a counter, not an accumulator. So at each iteration of the loop, you could ask the user if there is more data to process. And so we need to preset it to yes to go through the loop the first time. Okay. Now again, we're not going to, we haven't come to any version of this that we're ready to settle for. Okay, so keep an open mind. All right, and this is an imperfect solution that we're going to visit and go past. So let's see, we're setting a variable more data to yes, and we're going to say while more data is yes, get the next data item, process the item, ask the user if there is more data. So combining the interactive loop pattern with accumulators for sum and count, with an accumulator for sum and a counter for count, initialize the sum to 0, initialize the count to 0, set more data equal to yes. While more data is yes, input a number, he's calling it X, add it to the sum, add 1 to count, that's why it's a counter, ask the user if there is more data. Okay, and then sooner or later the user is not going to say yes, they're going to say no, for instance, in which case it's not going to pass the while test. Okay, and then we're going to drop through, and then we're going to create the output right here. I don't know why it wants to do that. Output sum divided by count. Okay. And that's what he's got here. Okay. Now he does have a trick. Okay. And you'll see people do this in programs sometime, where when they're asking the user for some kind of a yes or no response, they'll only check the first character of the string that they get back. So here we're saying more data is a string, right? And so we say, well, the first character, the 0th character of that string is equal to a lowercase y, well, then we do the body. And then at the bottom, we say, do you have more numbers, yes or no? Okay. And of course, when they finally put in no, the first character isn't going to be a y, it's going to be an n, and that's going to be, we're going to get what we want. Now, what would that allow you to do differently? Well, it would accept a y, a yes, yeah. Okay? Again, this is a solution that we're going to pay a lot of attention to. So this is an interesting idea, but not the way we're going to solve our problem in the end. So let's see, enter a number, 32. Do you want more? Yeah. So the user, she can enter Y, yes, yup, Y again. Nah is enough to stop it. It's not really checking for no. It's checking for Y. And then it does that. Now, I think you probably know the reason why this is not a great solution. It's too busy. Okay, we're asking the user to to enter every number and then to say whether they're done or not each time. Too much data entry. So there's got to be a better version, and we're going to find our way to it. So the way we're going to find our way to it is a classic approach, a classic pattern called a Sentinel Loop. Now, what's a sentinel? Well, a sentinel, in the sense of people and armies and guards, a sentinel is the one who sends the signal. Okay. If we're some kind of army and we have a camp and we're all going to sleep, we'll post a guard to act as the sentinel. And when they see the enemy coming, they're going to say, the enemy is coming. They're going to wake us up to the fact that the conditions have changed. Okay, it's not appropriate to sleep. You have to get up, get your boots on, and get ready to fight the war again. Okay, so it is a sentinel in that sense. What we're going to do is we're going to have some value that's going to wake us up that it's time to end the processing. Okay, it's a special value. The special value is called a sentinel. It's what wakes you up. The sentinel must be distinguishable from the data since it's not processed as part of the data. So that takes some tricky thinking, but there are some very common ways to do this, and we're going to explore really all of them. So let's look at the pseudocode here. Get the first data item. while the item is not the Sentinel, process the item, get the next data item. Now, interestingly, we did have some things before with our while loop. We did have some things where we did some getting ready action. Okay, for instance, um, in the last version that we had, we set the variable to yes to make sure that we performed the loop at least once. Okay. Now what we're going to do here is we're just going to get the first of the data items, however we get it. Okay. Again, if we're processing the characters in a string, we're going to look for the first character in the string. If we're processing the items on a list, well, we're going to look for the first item on the list. If it's the lines in a file, where we're going to try to read the file and get the first line in the file. Okay. What this does is this gives us an opportunity to determine that we don't have the Sentinel. Okay. Those things I really talked about. That's more checking for the end of the list. So I kind of spoke out of turn there, but it's a similar concept. One of the things about getting data from the user at the console using input is the data never seems to run out as long as your user will continue to type when you prompt them. So in this case, it's more important to think of this as we can prompt the user forever, and we're going to keep doing it until they give us a special value. So the first item is retrieved before the loop starts. This is sometimes called a priming read, since it gets the process started. If the first item is the Sentinel, the loop terminates and no data is processed. Otherwise, the item is processed and the next one is read. So with the Sentinel, it is possible for us to detect the end of the input even before we get any usable input. The first time that we prompt the user, they can give us a Sentinel value. So one of the things that I'm going to do in the programs that I'm going to have you create for this chapter is I'm going to have you assume that it's always possible to get no useful input. It's always possible to have an empty list of things to process. Okay. If you don't assume that, you can accidentally try to do things that will bring you harm. Like, for instance, if we're trying to add up a list of integers and we're going to try to find the average, which means that we're going to divide the accumulated sum by the number of integers input. Well, if we input 0 integers, well, that calculation is going to divide by 0, which is not defined, and will get us an exception. It'll throw a divide by 0 exception. Okay, so when we get to the end of these things, we're going to have to decide: do I simply want to print the answer, or do I want to check whether I had any input? If I didn't have any input, I'm going to warn you didn't give me any input. Otherwise, I'm going to calculate and print the answer. So because of the fact that as soon as you get to the Sentinel loop, you can have no input, no useful input. You always have to allow for the possibility of having had no useful input when you go to report the output. Having a hard time getting to the next slide. Here it is. So in our averaging example, assume we are averaging test scores. We can assume that there will be no score below 0. So a negative number will be the sentinel. Okay, so there are some sequences that we might want to process where there's kind of a natural value that it's possible to enter as the sentinel. Okay, so here we say that x is the float of enter a number negative to quit. So then we say while x is greater than or equal to 0. So if we get, as soon as we get a negative input, we're not going to do the loop anymore. If in fact we get one the first time we prompt, we're never going to do the work in here. Okay? Now, I just want to point out that this program is not up to my standards, which I'd like to be your standards, because it tries to print the average even if it didn't get any usable input. That's going to create a divide by 0 exception right here. Okay, so our programs are going to be more robust than this, right? Okay, so here's an example where we entered some useful data. So we've got 1, 2, 3, 4, 5 useful entries. -1, that's the sentinel value, and then we calculate the average. Okay, well that seemed to work pretty well. So this version provides the ease of use of an interactive loop without the hassle of typing Y all the time. Okay, it's much better. So that Y version where we type yes or no, nobody really does that. You know, do you want to input another? Do you want to input another? It's very annoying to do that. That is like, that's very unappealing interaction design. There's still a shortcoming. Using the method we're currently using, we can't average a set of positive and negative numbers. Okay, because the sentinel value has to be a value that, one, you can identify, and two, you wouldn't otherwise want to process. Okay, so if we do this, our sentinel can no longer be a number. So if we want to process a positive number, we also want to process a 0, and we also want to process a negative, then there isn't a number that can be entered that can serve as the sentinel. So we're going to have a more sophisticated approach. Well, guess what? We have one. We could input all the information as strings. Now, I just want to point out that that's the way we always input it. We could, I think what we're really saying is that we could delay the point at which we turn the string into a number, right? So when we do an input, we get back a string, okay? We usually wrap that inside of an int or a float to immediately convert the string to a number. Well, we could delay that. We could get that string and inspect it and see if it perhaps has a sentinel value instead of a number, okay? In which case, we'll know we have the sentinel value, okay? And one of the things that's very popular is the Sentinel value is just enter. It is the empty string. Okay. People, it's been popular since the early computing days, right? So here's the pseudocode for that. So we initialize the sum to 0, the count to 0. Input data as string. So we call this X string. Okay. Now, I just want to point out, for me, the variable X is a very bad name. Okay. So I would call this, I'd probably call it something like input string. Okay. So instead of exter, okay. And then I would be saying, while input string is not empty, convert input string to a number, and I wouldn't call it X, but I would call it input as number, okay? And then I would say add input as number to sum, add 1 to count, and then I would do the next input. So this is this is a very typical design, okay? So the loop, before you start the loop, you always read one time, okay? That allows you to detect right at the beginning of the loop if you don't want to processing, if you don't have any real data to process. If you got the Sentinel on your first read, well, then you're going to go right down to produce the output. Again, this is not sophisticated enough for me. We should have an if-else. We should be able to say, if we had a count of greater than 0, then we want to do this output. Else, then we want to politely say, you didn't give us anything to average. All right. Let's look at the next one here. Having a hard time with my slides. There we go. So here's the pseudocode turned into a program. Okay, and it has all the kind of stuff that we would expect. We are initializing the count and the sum. Okay, we are reading the input as a string. We're giving it, I think, a very unappealing variable name, but we're getting the input as a string. And the prompt says enter a number, and then in parens this enter, that means the enter key to quit. Okay, and then we'll say while the input string is not equal to the empty string, then we convert the input string to a float using float, and then we accumulate the sum, we increment the counter, and then we read. You always read at the bottom of this loop. Okay? And then again, instead of just printing, we should check if we have a count greater than 0, because we don't want to divide by 0. Okay? I think he just didn't want to confuse us, but this code is not robust enough the way it currently is. Okay? So let's see. 34, 23, 0, negative 25, negative 34.4. So he's using the whole range of numbers, which is great. It's only when he inputs the empty string or she inputs the empty string, that she gets the computed average. Okay. Okay. So, I'm just going to back up and say, I'm going to have you do a version of this kind of thing as part of your homework exercise assignment. Except that before I have you do it, I'm going to show you an example in a tutorial where we're taking this general approach. This is kind of the first approach that we want to keep, with the one where we're prompting at the console and we're expecting enter as the Sentinel, which is going to give us the empty string. The only thing that we're going to do is we're going to do a more sophisticated job at the end to make sure that we don't accidentally divide by 0. Okay, so this is the first kind of keeper, right? All the things that we looked at before were interesting ideas, but not really up to snuff. Okay, and this, with the correction in the final part of the program, will be something that we'll actually have you do. All right. Okay, now, the fact is that we have a lot of data processing. We have a lot of information processing where we're not in an interactive session with our user. Certainly, interactive sessions with the users are appealing for a lot of use cases, but there are times when we just have a bunch of data. These are data that have come from some process in our organization. We could be in retail sales. So they may have come from a cash register or a point of sale terminal. We could be researchers, okay? And these, some series of entries could have come from some sensor. A sensor that measures the temperature once per so many minutes, or it measures the height of the river in feet every so many minutes, right? So there are all kinds of processes that are not us trying to monitor a user at a console, but that just kind of generate batches of data inputs or observations that we're going to process. Okay, so we're going to learn how to do that. We've talked about this in the past. We talked about the batch model before, and we're essentially going to get to the point where we're going to process data using the batch kind of model, which means we have a lot of input when we start and it's in some kind of file. Okay? So the biggest disadvantage of the version that we're using so far is that it is interactive. What happens if you make a typo on number 43 out of 50? Yeah. A better solution for large data sets is to read the data from a file. Okay, so you could, for instance, put the data into some kind of a text file, and then you could run the program that processes that file, and let's see if you were able to detect some kind of a typo on 43, like instead of a number, you put in some kind of alphabetic. Well, then the program could detect that and print out some kind of an error message, and then the user could go back to the text editor and go to line 43 and fix that, and then run the program again. So here is a version that works with a file. Okay, so like some of the work we did in Chapter 5, what do we need to to process an input file? Well, we have to know the file name. Okay, and the file name can include the path information. You'll remember that the last thing that we did in Chapter 5 is we used tkinter to pick the file graphically rather than by typing in the name and the path. That's always a possibility too. But we get the file name and then we open passing the file name and in this case the indicator that we want to read, and we get a reference to the file in this in-file variable. Okay, and again, because text files are sequences of lines, we can use the for-in construct. So we're doing the initialization up here. Sorry about that. It doesn't want to cooperate. So and then we say the for-in. So for line in file, so we say we're assuming we're going to have one number per line, okay? And we say, well, the sum which we had initialized to 0, sum equals sum plus, and then we just going to convert the entry that's on the line to a float. Now you might say, Kevin, you might have a lot of extra spaces on that line. And I would say to that, float's pretty robust. Okay, it's pretty smart. And as long as all you have on that line is a proper number and spaces, it'll work just fine. Okay, and then we increase the count, and then of course, when we're done with the entire file, then we print the average. And again, we've got the same problem here. This doesn't work when we don't have any input because it divides by 0. Oops. Okay. Okay, so many languages don't have a mechanism like for-in, for looping through a file like this. Rather, they use a Sentinel. Okay? So there's nothing wrong with using for-in with a file. It's a very elegant way to read all the lines in a file. But we want to teach you the other way to read a file so that when you're using technologies that don't support for-in, you can, so you know what the logic pattern is without for-in to read a file. Okay? And again, files are simply sequences, so it being able to look for the end of a sequence by getting a Sentinel value is an important thing. Okay, so one of the things that we can do when we're processing a text file is we can use the method readLine in a loop to get the next line of the file. At the end of the file, readLine returns an empty string. Okay? So that's how we know when we're not using for-in for our text file. We're using readLine to read the lines. Okay? And what are we checking for? We're checking for the empty string as the Sentinel. Okay? That could happen the first time we readLine. Why? Well, because it may be an empty file. Now this is a trivial case. I mean, how many times are you going to have an empty file? Well, I can tell you from experience, often enough to get you into big trouble. Okay? So we're going to look for the Sentinel that can happen on any one of the read lines that we're doing, including the first one. Okay? So here's how we would do this. We would have a priming read, okay? So we'd have a read line, and then we would say while line, we're doing the read line into a variable called line. And we say while line is not equal to the empty string, process the line, read the next line. So if in fact the file is empty, you'll never do the body of the loop. You'll just go right to your end processing. Okay? If you've got a line or two or three, well, you'll process the line and then you'll read the next line and then you'll come back and you'll test. It's really very, once you get this pattern where you have this priming read before your while loop, and as for the while, you're checking for the sentinel, and then at the bottom of your body for the loop, after you've done all of your work, your processing, you do another read. This is like classic design. Okay, this would serve you very well. This will serve you very well for a long time. Does this code correctly handle the case where there's a blank line in the file? Yes, an empty line actually ends with a new line character, and read line includes the new line. Okay, so we won't confuse a blank line, a line that doesn't have any characters on it, for the end of the file, because the minimum that we get when we do a read line is we have a new line at the end. So these blank lines that don't look like they have anything in them when we're looking at them in the text editor actually have a new line on every one of those empty lines, which means that they're not going to prematurely signal end of file to us. Make sense? So here's one of this design where we're reading through a list of number inputs, and we are instead of doing it the really elegant way with the for in, we're going to learn how to do it with the read line. So the code up here, where we prompt for the file name, we open the file, that's the same. The code where we initialize our two working variables, that's the same. Here's the part where we do our priming read. Okay, you do that one time before the while loop. Then we have the while loop checking for the empty string, which is the signal that we get when we're reading these text files that we have reached end of file. And if we haven't reached end of file, then we're going to process the line. That's these two lines here, the one that begins with sum, the one begins with count. And then the very last thing that we do is we're going to do another read. Okay? And again, this is great except for the fact that if we don't have any input at all, we divide by 0. So all of our programs that we're going to do as a class are going to be just one step more sophisticated than this. Okay? Okay. Now, the next subject we're going to talk about are nested loops, which are loops within loops. Okay, so in the last chapter we did, chapter 7, we saw how it was possible to nest if statements inside of each other. Okay, and if you remember, the use case for that was we had some complex logic, And we wanted to break the decision down into levels of decision making. And that helped us out. Well, it turns out that we can nest loops inside of loops. So we can have a while inside of a while. We could have a for inside of a for. But it turns out for our use case here of processing sequences, the while inside of a while is really powerful. So what's it going to allow us to address? Well, it's going to address a sequence inside of a sequence. Okay? So suppose we change our specification to allow any number of number entries on a line in the file, separated by commas in this case, rather than one per line. Okay? So what happens then? Well, we have really two sequences. We have a sequence of lines, okay, and then on each line we have a sequence of number entries on the line. Okay. Now, if we write our code in a really elegant way, a really thoughtful way, we're going to be able to handle all of the possible lengths of the sequences. Okay, this is my goal for you. Okay, so in terms of what the code that we have so far, where we have one number entry per line, okay, well, we can deal with it if we have one line. We can deal with it if we have more than one line. We could have 100 lines. It would process it well, the code we've already done. The code we've already done also works if we have 0 lines, if we have an empty file. Okay, so it's very robust, thoughtful code. Okay, now when we go to process the number of entries on the line, now that we changed the specification, I would like our code to again be robust and thoughtful, such that I would like us to be able to process it if there's one entry on the line, if there's more than one entry on the line. I would like us to do the right thing even if there are 0 entries on the line. Okay? And just by being able to write this looping code in a thoughtful way, we're going to be able to write a program that's very, very resilient. Okay? So that if it turns out if a user puts in a blank line, we're just going to skip it. And if a user, it gives us 100 entries on one line, we don't care, okay? We're just processing the entries. We're a computer. We don't get bored or tired. We just keep going. And if they give us a handful of numbers on each line, well, then that's going to be the average case. We're going to be very good at that. Okay, so that's our goal. So at the top level, so we're going to have 2 levels of loop. You could call it the top level loop and the lower level loop. A lot of times you hear people say the inner loop and the outer loop. Okay, the top level is the outer, the bottom level is the inner. So at the top level, we'll use a file processing loop that computes a running sum and count. Okay, so let's see. It's just the same as the last one that we did. We're doing the prime for the read line. We're checking for the empty string as the end of file. The body of our loop, the work that's in it, is just this line, because this is kind of pseudocode. Okay, so whatever we have to do for the body. And then we've got the read at the bottom of the body of the loop. And then we're calculating the average in a kind of a dangerous way at the end. Okay, so let's look. In the next level, which is the bottom level or the inside, we need to update the loop. We need to update the sum and count in the body of the loop. See, since each line of the file contains one or more numbers separated by commas, we can split the string into substrings, each of which represents a number. Okay? If you really want to be good, and this is my eventual goal, I even want to properly handle a line that doesn't have any numbers on it. So when you split the string and you get back a list, the list is empty. Okay? Then we need to loop through the substrings, convert each to a number, and add them to the sum. We also need to update count, right? So count is not count of lines so far. It's been count of, observations, input, numbers that we're processing. Okay, so if we've got 4 of them on a line, we're going to need to bump that up 4 times. So it seems to me that we're going to be doing the counting of the numbers and also the accumulating of the numbers. That's going to go on inside of our inner or lower level loop. Okay, so we say for X string and line split on a comma. Okay, we did say that there would be commas between the entries. Sum equals sum plus float of X string. Now, again, I think that X string is a horrible name for a variable. First of all, I don't like X to start, and then Xter is a little bit too terse. So I guess we're saying it is the entry. I would call this entry as string. I would say for entry as string in line split, and then I would say sum equals sum plus float of entry as string. And then, of course, we're going to bump it up by 1. Now, I just want to point out that this is going to work just fine if there aren't any entries on the line. Okay, because what we're going to say is for each entry on the line, this creates a list. If the list is empty, we're not going to do this. So this is going to work for the unusual case where we have a blank line. We don't have anything on it. Okay? It is empty. Notice that this for statement uses line, which is also the loop control variable for the outer loop. Now this is pretty common. Okay, the outer loop and the inner loop have to have some way that they communicate with each other. They have to have something in common. Okay, and what's happening is the lines are kind of being created by the outer loop, and they're being digested by the inner loop. Okay, so let's look at this as code. Okay, we're doing the same things with the file name. And then we initialize the variables. We do our priming read. Okay. Now here's our loop. We're checking for end a file. Okay. And then we're turning this comment to update the sum and count for values in the line. We're using that as a comment, and we're actually implementing it. We took that code that we just saw and we plunked it right there. And then, of course, we have the read line at the end. Okay, so this is pretty robust code, except for the fact that we can divide by 0. Certainly the line processing, the processing of the entries on each of the lines is working quite well. So the loop that processes the numbers in each line is indented inside of the file processing loop. So the inner loop is inside the body of the outer loop, right? Well, the print isn't in the outer loop, but it just doesn't seem to highlight what I want to highlight, right? Okay, so this is the outer loop, the while, and this is the inner loop. And how do we know that the inner loop is inside of the outer loop? Well, it is indented like everything else that's in the body of the outer loop. The outer while loop iterates once for each line of the file. For each iteration of the outer loop, the inner for loop iterates for as many times as there are numbers on the line. When the inner loop finishes, the next line of the file is read, and this process begins again. So here's some comments on how to design nested loops. So you design the outer loop without worrying about what goes on inside. Then you design what goes on inside, ignoring the outer loop. Put the pieces together, preserving the nesting. Okay. And typically, the logic in the outer loop and the logic in the inner loop are going to share at least one variable. In the last case, it was the variable line. Okay, so we use that in the outer loop, and we also process it in the inner loop. Okay? Okay. Now, we're going to change gears a bit, and we're going to start to talk about Boolean values. We talked about them a little bit in Chapter 7. So both if and while use Boolean expressions, okay? Boolean expressions evaluate to true or false. Usually they are comparisons. So far we've used Boolean expressions to compare two values. So we said while x is greater than or equal to 0, for instance. Sometimes our simple expressions don't seem expressive enough. The decision is just more complex than that. So again, as the good mathematician that he is, Zelle's going to go right to math. He's going to go to geometry, and he says, well, what if we're dealing with points in a plane that have x and y coordinates? So what if you have to test two different things in order to evaluate your circumstances? Well, there are all kinds of things, all kinds of situations where you need to test more than one thing without having to think about a Cartesian plane. Okay, but that's his first example. Okay, you might not just be testing a single value. Okay, so he's got these two objects. One's called P1 for point 1, the other one P2 for point 2. And they store both X and Y coordinates. This is part of a custom class that represents a point on a Cartesian plane. So he says if get X, if you get the X coordinate from point 1 and it's equal to the get the X coordinate for point 2, then then he compares the Y's. If both the X's and the Y's are the same, their points are the same, else they're different, else they're different. Okay, so that's how you would do it with if else. If you had two values you had to take into consideration. Clearly, this is an awkward way to evaluate multiple Boolean expressions. Yeah, whenever you have a code that kind of looks like this, I would call this kind of code inelegant. It's kind of bulky. You look at that and go, that doesn't read like I think. Okay. And the ideal things when we're working with these Booleans is we'd like to get them to the point that after we learn how to craft them and we learn how to read them, they kind of read like we think. So how do we get more powerful, more expressive Boolean expressions? Well, we take the Boolean expressions that we know already and we find a way to combine them using the operators and, or, and not. Okay? So let's just see how we're going to do that. So the Boolean operators and and or are used to combine two Boolean expressions and produce a Boolean result. Okay? So on the previous slide, the only way that we were able to combine these was to create a nested if. We can do it a little more explicitly if we're going to use, in this case, we would have used and. Okay, so we can say expression and expression, or we can say expression or expression. Okay, now, to me, this kind of table that we see, which is called a truth value table, or a truth table, these are really old school to me because I was a philosophy major and I took a number of symbolic logic courses, and we created these things as we learned about symbolic logic. So if you've had that kind of thing, you'll look at a truth table like this and you'll go, oh, this is great. I understand this immediately. If you're new to them, then it's going to be helpful for me to explain them. So P and Q are two typically logical propositions. Okay. In this case, these are Boolean expressions. So we have a Boolean expression P that's on the left side, and a Boolean expression Q that's on the right side. And if we say P and Q, in what the situation is the combination P and Q going to be true, and when's it going to be false? Okay, so if P is true and Q is true, then P and Q is true. In all other cases, it's false. So if the one on the left is true and the one on the right is false, it's false. Vice versa, it's false. If they're both false, it's false. So P and Q is only true in the case where P is true and Q is true. Okay? Makes sense? All right. let's go to the next one. Okay, so, here's some of his commentary on that slide. So in the truth table, P and Q represent smaller Boolean expressions. Since each expression has two possible values, there are four possible combinations of values. The last column, it gives the value of P and Q for each of the combinations. So again, four possible values. These are all the permutations that you can get when you combine two things. Four, okay? And again, with P and Q, the only permutation that works is when P is true and Q is true. Okay, that's the only one that's going to turn out where the expression P and Q is also going to be true. Let's look at P or Q. Okay, so if we're doing OR, this kind of way of filling out the truth table where we go true, 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 false, false, true, false, false. This is the typical sequence that you see. Okay, there are four values. Okay, there are four scenarios. Scenario one, they're both true. Scenario two, the left one's true and the right one's false. Scenario three, the right one's true and the left one's false. Scenario four, they're both false. It turns out that P or Q gets the exact opposite answers. Okay, so P or Q is only false if they're both false, and it's true in all the other cases. And somewhere in a slide here soon, we're going to say that this is an OR that's not the OR that we use in everyday English. I think it's on the next slide that we say this. Yeah. So we say the only time OR is false is when both expressions are false. Also, note that OR is true when both expressions are true, which isn't how we usually use OR in conversational English. So the example that I typically use is, let's say we have a company picnic, okay? And we consider that kind of an obligation to go to, right? You have to show up, you have to act like a good employee, and maybe you'd rather be doing something else. You'd rather be hang gliding or scuba diving or playing golf or reading a book or sleeping in all day. All right? Okay, so let's say we've got two people who work for the company, Kevin and Alice. Okay? If we say to the boss, the boss comes into our department, Kevin and Alice, and says, "Are you guys coming to the company picnic on Saturday?" And we turn around and say, "Well, either Kevin or Alice will go." Then the boss is going to leave there, given the meaning of typical American English. He's going to think, well, Kevin will come and Alice won't. Or Alice will come and Kevin won't. Okay? But they won't both come. And they won't both not come. So that kind of OR that we use in kind of everyday speech here in English is called the exclusive OR. Okay? It's only true if one of them are true. In symbolic logic and in computer programming, we use an OR that we call the inclusive OR. And in the inclusive OR, it is true if they're both true. It's true if one's true and the other false. It's true if the truth is the other way around. Okay? The only time it's false is when they're both false. So in this kind of logic, if both Kevin and Alice came to the picnic at the same time, no one would be surprised. Where in our way of everyday speaking, people would be surprised. They would say, I thought only one of you were coming. Because that's what we mean in everyday talk when we use or. Okay? Not the case here. Okay? Or it's going to be true if they're both true, or if one of them is a true, or is only false when they're both false. Okay? What about not? How does not work? Well, not works on one operator, okay, and it creates the opposite, okay. So let's say that we have one expression, p, and we want to know what not p will be. Well, if p is true, not p is the opposite. It's false. If p is false, not p is the opposite. It's true. Okay? Now this is, as we say that not is a unary operator, meaning it operates on only a single expression, which is why when we only have one column here. And why do we only have two rows? Well, there are only two permutations of the truth. There's one where it's true and the other where it's false. If you have two things, like we did before, there are four possible combinations. If you have one thing, there are only two possible combinations. And so not p is always just the opposite of the truth value for p. Now, we can put these operators together to make arbitrarily complex Boolean expressions. The interpretation of the expression relies on the precedence rules for the operators. So we're going to talk about the precedence rules for the operators, just like we did for the precedence rules of operators with math. But you won't be surprised to hear that I don't want you relying on the precedence of logical operators any more than I wanted you to rely on the precedence of mathematical operators. So consider the expression A or not B and C. How should this be evaluated? Well, again, I'm going to say this again. If you're on my team and I find code like this, I'm going to call you up and read you the riot act if I find code like this, okay? So the order of precedence from high to low is not and or. So we group first with not, then and, then or. So this is equivalent to, in the middle, not be, okay, that not be and C, so that's has the second amount of strength, and then A or not B and not C. It's hard enough to understand these things with the parens in, so please put the parens in. Okay? Even Zelle wants you to put the parens in. Okay, so the test for collocation of 2 points. So again, this is planar geometry where these points have two coordinates, x and y. Okay, and when the two x's are equal and the two y's are equal, then they represent the same point. Okay, high school geometry. Okay, I told you wouldn't have to do high school geometry, but to read his slides you do. To pass my version of the course, you don't. Okay, so we say if the x's are equal and the y's are equal, then the points are the same, else the points are different. The entire condition will be true only when both of the simpler conditions are true. Well, why is that? Well, because it's an AND. Okay? And if you think back, how do ANDs work? Well, the only time an AND is true is when the thing on the left is true and the thing on the right is true. In any other case, they're false. Okay? Okay. Now let's get away from Euclidean geometry and into something more fun like games. Okay, so let's say we're writing a racquetball simulation game. The game is over as soon as either player has scored 15 points. And I guess that those are the rules for racquetball. I haven't played racquetball in 30 years. How can you represent in a Boolean expression? Well, score A equal 15 or score B equal 15. Okay. When either of the conditions becomes true, the entire expression is true. If neither condition is true, then the expression is false. Okay? So, if one of the players has gotten to 15, then the game is over. If the other has gotten to 15, then the game is over. It can't really happen in racquetball, but if they both got to 15, then it would be over as well. I just want to point out something here. I wouldn't have written this slide this way. I would have said score A greater than equal to 15 or score B greater than equal to 15. One really nasty trap that you can get yourself into is looking for the situation where you've gotten just exactly to the end condition. Well, what if you're past it? Okay? It's usually safer when you're checking for end conditions to check for something like greater than equal to 15. So if it ever happens that that you go past it, and I don't know how exactly you're going to go past it, but that's it's sort of a safer way to check things than what we see here. So we want to construct a loop that continues as long as the game is not over. Well, that would be saying we're writing a program to simulate a racquetball game, okay? And it's going to go around the loop, probably offering each person a turn until the game is over. So we're going to do it while the game is not over. So you can do this by taking the negation of the game over condition as your loop condition. So we say while not score A equal 15 or score B equal 15. And while that's, then we're going to continue playing. Okay? All right, I think that makes sense. Some racquetball players also use a shutout condition to end the game. That's where you don't get quite so far on, but one of the lower player has 0 points. So if one player has scored 7 points and the other person hasn't scored yet, the game is over. Okay, so what do they do here? They say if it says while not, and then we have all the conditions in which the game might be over. Okay, so score A equal 15 or score B equal 15. Okay, that's the first grouping. Or score A equals 7 and score B equal 0, or the other combination. Okay, so while we haven't reached any of these three possible end conditions, continue playing. Okay. Oh, let's look at volleyball scoring. Now, I played volleyball a little more recently than racquetball, but it's probably 25 years. To win, a volleyball team needs to win by at least 2 points. Yeah, I kind of remember that. In volleyball, a team wins at 15 points. If the score is 15-14, play continues just as it does for 21-20. So let's see, we could test this. If A is greater than equal to 15 and A minus B is greater than equal to 2, or if B is greater than equal to 15 and B minus A is greater than equal to 2. Or we could say this. If A is greater than equal to 15 or B is greater than equal to 15 and the absolute value of A minus B is greater than equal to 2. Now, I've got to say that this second version, because it's shorter, I think it kind of appeals to me more than the top one. Okay. I think they're going to do the same thing. So let's go on to the next slide. So we have this thing called Boolean algebra. Okay. And Boolean algebra is a symbolic logic system for combining logical expressions. So the ability to formulate, manipulate, and reason with Boolean expressions is an important skill, especially for programmers. Boolean expressions obey certain algebraic laws called Boolean logic or Boolean algebra. Okay. So we're going to go explore that a bit in the next 5 slides, maybe 6 slides. Okay. One of the things that is pretty important to be able to do is to simplify these expressions as they show up in your program. There are times when if you just use the first kind of expression of the conditions, people after you, or even you when you come back to it, you look at it and you go, well, why am I doing that? Why do the conditions look like that? So it turns out it's possible to simplify expressions, and most of the things we're going to explore on the next couple of slides have to do with rules that help us to simplify expressions, that help us to leave behind code that's easier to read than the original expression would be. And as I mentioned just a little while ago, that's good for the people who come after us to maintain our code. It's also important for us. I know for me, the dividing line is always about 1 year. If I come to my code after a year, it looks pretty much to me like somebody else wrote the code. Okay? I'll look at it and I'll go, well, gee, that's a great job I did. Or, that's a disappointing job that I did. But I don't remember writing it, right? So the person who maintains the program might be you. So this ability to understand some of this Boolean algebra and to use it to simplify the expressions that we leave behind in the programs, that's going to benefit anybody who has to maintain the program later, especially good if that person is you. Okay, so let's see. So in algebra, if we have some quantity a times 0, it's equal to 0. A times 1 is equal to A. A plus 0 is equal to A. So in Boolean algebra, A and false is equal to false because they both have to be true, right? So as long as you have one false, you know that anything and false is going to be false. A and true is going to always be equal to A. Okay, because this is only going to be true if the right side is true and the left side is true, right? So if we know the right side is true, then whether the whole expression is true is all riding on A. So A and true is the same as A. A or false is the same as A. Okay, because with an or, we know that if one side is false, then the only way it can be true is for the other side to be true. So again, it's all riding on A. Okay? So it says, and has properties similar to multiplication, or has properties similar to addition. 0 and 1 correspond to false and true, respectively. Now, I just want to pause here and talk a bit about true and false and 0 and 1. Okay? So in the Python code that you write, if you are trying to test for true, test for the literal value, capital TRUE. And if you're trying to test for false, test for the literal value, capital FALSE. Okay, those are the official values. We're going to learn in a minute that in some circumstances, it's possible to test non-Boolean variables in a way that generates a true or false. But in terms of code that we create, it's impossible. It's very, we shouldn't be treating zeros and ones as a kind of, equal alternates for true and false. The real values are true and false, and that should be important to us. Okay, so Boolean algebra. So anything ORed with true is true. Why? Because only one has to be true. And if we know that the right side is true, then the combination is always going to be true. Both and or distribute. You kind of, will remember this from your arithmetic. So A or B and C is the same as A or B and A or C. Okay? So it picked up each one. A and B or C is equal to A and B or A and C. Now, why would we want to do these? We would want to do these in order to find a way to simplify the expression we leave behind so that it's easier to read and understand, to get the expression closer to the mental model of the reader. Double negatives cancel out. So if we say not A, it's equal to A. I think we're used to that. I don't know if you used to say this, but when we were kids, we used to, somebody used to say double negative, and you go, oh, that's a double negative, right? So, I mean, we were pretty young when we were doing that. So I'm thinking that we all know that double negatives cancel each other out and you get a positive. Now, this next set of Boolean algebraic truths is really powerful, and you can really use it to simplify um, code. Okay, so for instance, you can take a not A or B, and it turns into a not A and not B. And you can take a not A and B, it turns into a not A or not B. Now these properties, these laws, these kind of rules of Boolean algebra, were first popularized or brought to light by a person named De Morgan. So they're called De Morgan's laws. The ability to go from one expression here on the left or the right to the other one, it turns out to be pretty powerful. There are times when you have, let's say you have a while loop, and you're looking for, you want to say while not A or B, it might read better as while not A and not B. Okay, or vice versa. So these are, again, you can use all of these things as simplifications. And the goal is to leave behind code that you and your colleagues will find easy to read a year from now, and because it's closer to your mental model of the problem at hand. Which is what we say here. So we say, if we're saying while not score A equal 15 or score B equal 15, we can change not A or B to not A and not B. Okay, so while not player A has gotten to the end of the game, and not player B has gotten to the end of the game. Okay, so to me, the second version here rings truer with my thinking. Okay, what do I have to check? Well, I have to check that player A hasn't gotten to the end of the game and player B hasn't gotten to the end of the game. As long as those two things are true, we can keep playing. Okay, whereas up here, this seems more vague to me. Okay, so this is an application of De Morgan's law, which is one of the more powerful principles of Boolean algebra. So that seems pretty highfalutin. On the other hand, you come back here and you say, oh, wow, I like the second version of that code infinitely better. It really plays well in my head. That's what we're looking for. Okay. So this becomes while score A not equal 15 and score B not equal 15. Isn't it easier to understand? Well, I've just been telling you that I think it's easier to understand. Okay. So what's really true here is you have to understand these logical principles in order to predict how your code's going to work, and also some of these finer points of Boolean algebra, in particular De Morgan's laws, will help you to simplify the Boolean expressions in your code so that they're easier to read. They're closer to your mental model. Now, here's another case where you could use De Morgan's law. Sometimes it's easier to figure out when a loop should stop rather than when the loop should continue. In this case, write the loop termination condition and put a not in front of it. After a couple of applications of De Morgan's law, you are ready to go with a simpler but equivalent expression. Right? So there are times when the end of a racquetball game is pretty simple to conceive of, but you may be doing something that has a lot of parts, and you may only be in fact, it might be easier to describe when you want to continue. When you want to stop rather than when you want to continue. And so you would write the condition for when you want to stop and surround that whole condition with a not. Now, you might wind up with a really thorny expression there, but you can take the principles of Boolean algebra, and again, in particular, De Morgan's laws are pretty powerful. And then you can take that expression and simplify it and wind up with a while expression that's pretty easy to understand. Okay. Other common structures. All right. So we have come to the end of part one. We all deserve a break. Okay. When we come back, we're going to be picking up here on slide number 69. And I'll see you there in just a few minutes. Bye for now.